Hello, greetings to everyone online here tonight. We do apologise for the delayed start here, but delighted to say that we look like we're back on track now. I think our presenter, and you've got a very good one this evening, Sanjeev Meston, I can think of actually no one better in this country to be talking to us about coding. I've seen a few of Sanjeev's presentations on this. Newton's method, iteration, you know what, I reckon I'm reasonably okay with that. But the coding stuff I can do a little bit, but not a lot. So we've got a good presenter for you here, Sanjeev. I think his phone line must have been underwater at some point, but I'm delighted to say that we're on track now. So I'm hoping you can all hear me. Can you hear me, Sanjeev?
Yes, I can. Yeah.
And you know what? We can hear your lovely voice as well. So
Okay,
my name's Brian. I'll be in the background for comments and questions. If you are posting questions, please just post to everyone so we all get to share the love and see what's going on. I will hand you over to Sanjeev. Thank you.
Thank you, and welcome everyone. And sorry for the delay, but nevertheless, we are all back online, and we'll get started. So that's me. Brian has already introduced me, and that's a static screen I've got. So I'll be running most of my presentation using PowerPoint. So you can actually see I've got a function there, and I'm starting with an initial point there, which actually I'm going to demonstrate. And that initial point from the curve, from that point I draw a tangent, determine the x-axis for the x-intercept for the tangent, and then use that point and draw another tangent, determine the x-intercept, and you'll see these red dots actually get closer to the solution point. That is it. So it's a recursive pattern, and we are making sure that the x value gets closer to that actual solution, which is point A. So I'm going to demonstrate that here. So at the moment, what I've got is I've just started from a random pointer. I'm just going to demonstrate that. So that's my first x point, and then I take the function value there. And from that particular point, I draw a tangent. And wherever the tangent intersects the x-axis, that becomes my new x point. And then from there, I use that new x point and draw a tangent from the curve. And you will see that these tangents actually start getting closer. So I'll give you a demo now. So I'm going to move the point, and you can see how the tangent and the position of the tangent is actually changing. And the more colored lines are actually the tangent, and they're actually getting closer to the solution, which is the actual point. So I'm just moving that. Now, this can all be done on the CAS, and I'm going to show you how you can actually set it up on the CAS in a moment. So that's really my solution. And in this case, it's saying with 3 iterations, I've actually got to the solution. So with Newton's method, actually, if you select the correct point, you can get to the correct solution in as little as 3, 4, or 5 iterations. It really depends on the initial point that you have selected. Okay. So this is the algebraic method for the recursive pattern. So what we need is the slope of the tangent. And you can see on my screen. Brian, can you just confirm that nothing is obstructing the screen?
No, screen's good, mate. And yeah, I was just starting to type into the chat. This looks familiar to us. So we are familiar with Newton's method, so that's good. Yes, but I love your graphics there. Very helpful.
Yeah. So what we are doing is basically the formula for slope, y2 minus y1 over x2 minus x1. And we are actually getting the gradient at that point. And we have just rearranged the formula. So I is my initial point, x1 is my new point. If I rearrange this formula, I actually get to this state. And this is the iteration. So that's my initial point. And then my new point, x1, is simply the initial point minus the function value at the initial point divided by the derivative. And then if I continue this recursive pattern, then x2, my second solution, comes from the first possible x value, which is x1. And since it is recursion, I can go to n terms. So I've got n plus 1. My solution would be dependent on the previous x value, which is xn. So that's the general formula. So if we kind of analyze the formula next, so I'll just show you how to set up the recursion pattern there. So I just typed in a function. Now I've actually put it on a little fast forward so you can see that I've just created a square root function, and I'm just adjusting the window size. Now I'll go and select an initial point using the geometry application. So I just selected a point, and then I'll put the coordinates for this point, which are 5 and 0. Now from this point, I'm actually going to draw a perpendicular. So construct a perpendicular, and this perpendicular should intersect the curve. So I determine the point of intersection, which I'm going to do now here. I'm trying to change the color there. That's not really necessary. So point of intersection. Now from this particular point, I need to draw the tangent. I'm using the geometry application, and there's this option to draw a tangent. And this tangent now crosses the x-axis. I can change the color of the tangent. I've changed it to green. I'm going to number it to 1, and the next tangent likewise would be 2. So from this point where it intersects, I draw another perpendicular to the curve. That's my perpendicular, and wherever the perpendicular intersects the curve, I'm just trying to change the color there to red. And now I'm actually going to draw the tangent from this new point where it intersects the curve. So I'm just changing the color and making it a dotted line. So I draw my second tangent, and I'll call it tangent 2, and I'll just change the color to green for that one. So that's my second tangent. So all I've used for this is the geometry application. So all the tools are sitting under geometry there. So I've just labeled it as 2. Now I can repeat the process, get the third tangent, and at times you may just need to adjust the window size so you want to see everything better. So I've got the third perpendicular, and now I'll do the tangent at that point by after changing the color and the attributes, because I just want all the perpendicular lines to look dotted and red. That's what I've just done. And lastly, I'm going to draw the tangent at this new point and change the color to green, and that would be my tangent there. So that's how you can actually set it up. And now that point that I selected initially, I can drag that point there. So this is the logic that we have used. So all we are saying is we really need 3 values for each recursion step. And so if I look at the first iteration, it's the start value x0, the function value at x0, and then the derivative at x0. And then I go on to the next value x2, then x3. So x3 depends on my initial value x2. So likewise, my final iteration xn plus 1 would depend on the initial xn value. So that's something that I'm going to call Newton's rule for the rest of the workshop or the webinar, because I'm going to use that often. So I'll just refer to that as Newton's rule when I go through that. So I just want to do a quick analysis before we actually look at it. So on top over here, I've actually got the Newton's rule. And we are asking a question, when will xn plus 1 equal xn? Now that would actually happen when this part over here approaches 0. Now it's not actually going to become 0, it's going to approach 0. So we want the function value to approach 0. Now the function value could be a positive y value or a negative y value. That's why I put it under the absolute notation, but we want it to approach 0. And I have actually put a tolerance because it will never get to 0. So when should my iteration stop? I need to put a tolerance. And I normally use 0.00001 as a tolerance, which is pretty good for solutions. And we could run into a few problems now. So if I analyze the formula, if my denominator becomes 0, I'll get undefined. So my derivative which is the denominator, should not become 0 because I'll get undefined. That's the first problem that I can run into with Newton's rule or the method. The second problem could be the function value, instead of approaching 0, actually increases. It starts increasing. And in that case, my solutions actually are diverging from the original solution. They're not converging to the solution point. So the y values actually move away from the x-axis. So that would be a problem as well. And lastly, we could have the y value increases once, then decreases, then increases. So it actually sets itself into an oscillation mode. So we have to be very careful in selecting our initial point. So these are some of the problems that we could actually have with Newton's method. So I'm going to first of all demonstrate a very simple way of doing this on the calculator screen without any coding or anything. So let's see what can happen here. So I'm going to run this now. So I'm going to define a function and the normal method of storing or defining or assigning. So I'm just going to show a function, and I'm just going to do x squared x cubed minus 7. And I'm going to actually set up an initial value. I'm just referring to that as b. That's my initial value. I'm starting with 4, and you'll see my initial value minus the function value at that point over the derivative at that point. And I'm going to store this value as new value of b. And you'll see actually it sets up a recursion. All I need to do is to keep clicking the enter key, and it actually set up a recursion. And I'm more or less at the solution. So I can stop there. So I actually got my solution in 4 hits over here. And you can see the last 2 actually repeated. So all I did was I used Newton's formula and stored it as b again. So it calculates and it stores the new value, and then when you hit the enter key, it actually starts the recursion process. So it's as simple as doing it on the calculator screen. So you don't need actually the list and spreadsheet option or anything, but I'll actually demonstrate that because obviously if it's an assessment, you may need the list and spreadsheet page because you need the x value, you need the function value, you need the derivative value, you may need all those values. Then the list and spreadsheet page comes handy there. Okay. So let's look at it again, and this time I'm actually going to store, you're going to use the initial value as 5, same function, and cube minus 7, and I'll start with the initial value of 5. This has got 4. And just repeating that screen, unfortunately. I can skip that here. And that's what it is. So let's skip that and move here. So now I'm going to use the value as 5. Yeah. And actually this time I'm storing these information in a list. So when I put the curly bracket, I'm just going to display all these bits of information. So the first one is the original x value, the initial value, the function value at v, and now I'm going to determine the derivative at v. Now you have to be careful with the derivative. You can't put actually the x v value over there. You have to find the derivative at a point. So you just can't put v over there initially. And then I'm going to use the rule for Newton's method lastly, which is the function value over the derivative. So that's what it is. And now from here onwards, I can actually store the values and repeat the recursion there. Okay. So if you remember, I just mentioned when you're fine-tuning the derivative, you can't do this what I've got in blue. You have to use the derivative at a given point, which is 75. But if you do the derivative at 75, then it's going to give you the value of 0. So that's not the correct thing. I've often seen people actually make that mistake. So just be careful with that one there. So I'm just going to show you the option to approximate your answer. You can use the round option with the derivative, and then I'm going to say round it to 8 decimal places. So in the bracket, I have the Newton's formula, and it's already got a value there. Now it's repeating the value because I haven't said store it to a new value. So I'm going to do that now, store it to a new V value, and then I can actually start running the recursion. So now it's going to give me the value to 8 decimal places. So that's really what it is. Yeah. I'm going to demonstrate the list and spreadsheet method now. So to use the list and spreadsheet method, I first need to predefine the function. So I'm going to use the note page to first define the function. And this time I'm just going to store a function on the note page. So you could put any function here. So I've stored x2 plus 3x plus 6. I've entered some notes. I've used my initial point as 1, and I'm saying display my answer to 8 decimal places. I've just activated that. Then there I'm saying that's my tangent, and then I want to store that rule. So it's giving me the derivative equation. Now from here, I actually go to the list and spreadsheet page. So I'm going to add a list and spreadsheet page. And my first column, I'm just going to call that the iteration. So ITE, and I'm going to actually generate those to a sequence. So I'm going to use the sequence command, and I want to go up to 20. So sequence, then n, comma n. The sequence uses the letter n there, and I'm starting from 1 and going up to 20. So it's just 20 iterations, but I don't have to go all the way there. So in my next column in B, I'm going to type in the x value, in C the y value. And then in column D, I'm going to do the derivative. So I'll just call it the slope. And then over here, I'm going to do the calculations using the Newton's rule. So right at the bottom, you can actually see I'm calling it as a new x value. And I'll put the formula later on. And my last column is test. And it says when it starts repeating the value, it will actually say true. So now in the x value is my initial x value, which I stored on the notes page. And because the function is already defined, so the function value is going to be the value in cell B1. So that's there. And then the derivative in cell B1. So I'm going to use the derivative that I've already defined, which is there, the tangent, and derivative at the initial value, which is 1, which is in cell B1. And the new x value is a calculation, which is going to use Newton's formula or the rule. So it's the value in cell B1 minus the function value divided by the derivative value, which is 6. And I can approximate that. I can use the round command with that, which I have done. I'll do that approximation there. And now I'm going to put a test over there. So I'm saying the value in cell E for me, which is the new value. So the difference between that and B1 should be less than my value that I put, which was 0.001. And now I just need to copy the cell value. And you can do all of them together, but I'm just demonstrating how the values actually keep getting updated. And that one would still be false. So now negative 1.5 to 1 will go there, which is basically the value in E2 there. And after this, I'll just fill up everything together once I've done this one. And yeah, so now I'm just going to copy go from X1 and just put all the values together. So now it will start populating it itself. And you see, all of a sudden, you see there's a 2 there. That's where actually the values will start repeating. And it's meeting my condition there, which I put for the test result there. So this file will be available to you, and the formula for test and everything, you will be able to see that. But that's a good way for students to realize where they should actually stop their iteration, because they don't need to show all 20 of them. So when I get to iteration 7 or 8, I can stop there as per this file there. So we just saw that Newton's method will not always work. So I'm actually going to demonstrate something here. So we are putting a function there, which is x cubed minus 3x squared plus 7. And I'm going to actually test a few different values. So the first value I'm going to test is 0, which actually happens to be the turning point, and I should get undefined over there because it's the turning point. So obviously when the initial value is 0, it's not going to work. I'm going to try another initial value. This time I'm going to try the value 4. And let's see what would happen if I use the initial value as 4. And I'm going to actually set up the iteration over here. So I'm storing the values xi. So it decreases, 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 increases, decreases, increases. And now you see it's actually gone into an oscillation mode, so it's not going to work. So this is the other problem that I can have. So you see it's just increasing, decreasing. So it's gone into a kind of an oscillation mode. So it's the same graph I'm demonstrating. So you can see when I move that point, and let's see, just moving that, you can see the number of tangents is increasing. Now at this stage, I've just gone horizontal my tangents, so undefined. And then again, if I start moving more to the left, you see a whole lot of tangents there, but it's not converging to my solution point. And I'll have a problem until I actually get to that point. So the moment I go past 0, then I'm closer to my actual solution point. So that's undefined as well. Now, if I go past that point, now you'll see actually my tangents start converging to the point. So selecting the initial point is actually very, very important. So this file was to just demonstrate that selection of initial point is key. So just checking at -3, and now you'll see I should actually start getting the solution. So it's moving towards the solution point. So selecting the key point is, or the initial point is the key. Okay, there is another method I'm going to demonstrate. It's the same function I'm going to use. So I'm on my notes page. So the same function I've used, and I'm using my initial value as 4 this time. No, actually it's a different function, sorry. It's 5x squared minus 3x plus 4, and it's got -x cubed. That's a different function. So I've stored Newton's rule as gx. So that's my gx function, and I'm starting with an initial value of 4. Now, this is a very handy trick. So I can just do g of x0. That's my first iteration. So you'll see I'm starting with 1, 2, 3, 4. So I've gone to the 4th iteration straight away just to demonstrate. And I get actually this value of 4.53284. Then I go to the next iteration. So you see each time I'm putting a bracket and putting g, and it's actually doing the iteration. So I do get a solution when the initial value is 4, and the solution is 4.53284 in this case. If I go to the next screen, I'm using the initial value as 2. And I've done exactly the same thing. I've stored the function as gx, that's Newton's rule. And you will see I've started with 4, the value was 1.47641. You can actually start with 1, 2, 3, 4, but I just wanted to save time, so I've just demonstrated that. But what you notice over here, the value decreases, increases, decreases, increases, decreases. So it's actually gone into the oscillation mode when x is 2. Now let's go and look at x equal to 3. And you will see x equals to 3 was actually a turning point, and you see I get undefined. So this is yet another quick way of setting up the iterations on the calculator or on the note page. It's better done on the note page. Now, I was earlier talking about how selecting the point is a key. So I've got this function tan inverse of x minus 3 over 2, and then it's undergone a vertical translation of 1 over 8 units. So the blue is the graph over there for the function. I've started with an initial point of 3 and 0, and you can see my first tangent there. Then I've got the second tangent, and if you look at the right side, you will see tangent 1 and tangent 3 have a negative, they're crossing on the negative side of the number line on the x-axis, and you've got this 4 over here and the tangent 2, they're crossing on the right. But each time, you see tangent 3 is moving away from tangent 1. Tangent 4 is moving away from tangent 2. So if I was to go and do a fifth tangent, it will go further away. And you'll notice that actually the x values are now diverging towards negative infinity and positive infinity. So once again, for this one, I can't work out the solution by selecting that initial point there. So moving on to pseudocode now. So I'm guessing you all have a very good understanding of what Newton's method is, but one of the new aspects in the study design is to be able to write a pseudocode, which basically is based on an algorithm that you are going to use to determine your solution or to solve a problem. So just to explain the pseudocode, it is basically putting all the information in form of text, your algorithm in form of a text, which is easy for anyone to understand. So you're not using any specific programming or coding language. Now, when you write a code, obviously there are certain set of instructions, and those instructions go in a set of multiple lines. So you could have 3 lines, 4 lines, 5 lines that could comprise the pseudocode. And when you execute all these instructions together, we say you are actually running a program. So set of instructions is actually called a program. So in the next few screens, we're going to look at writing a pseudocode for Newton's method, and then we'll go and test our code with certain programming applications that are available on the TI-Nspire. One of them is Python, and the other is TI-Basic. So there are 5 rules that you need to remember for the pseudocode. So the first thing is you only write 1 statement per line. And what that means is each of the statements only expresses 1 single action. You need to capitalize the initial word. It could be read, write, define. Those need to be written in capital letters. Then you need to use the indenting properly for loop, or if there's any other condition like an if condition. And if there are multi-line structures, then you need to have an end condition over there. And the last one is the each statement language independent. And this next screen actually explains what it is. So for instance, if you are using Python or if you're using basic TI-Basic, the way the for or the while loop actually works over there, the text is different, the way it's presented is different. So we don't actually need to be specific to a language. All I need to do is to write the word for or while, and that basically means that there's a loop that I'm running. So we don't have to use the syntax for the language. So that's basically what it means, keep the statement language independent. So we are not writing a pseudocode specific to any particular coding language. There are some keywords in the pseudocode, and we call them as the programming constructs. These also have to be written in uppercase. So it could be a sequence, it could be a case, it could be a loop, while loop, or you could say repeat this until this condition is met, or a for loop. And if you're using the conditions if then else and end if, all these actually need to go in uppercase. So this just explains what each one of them is. It's pretty self-explanatory. So this is the code we are going to use to explain Newton's method. So we start. The first thing is I need a function. So I define the function as fx. So you see define is capitalized over there. The next thing I also need is to define the derivative. So which I'm defining as gx. Then you require a user input. And the user is going to tell you what is the initial value they are selecting. You are going to put the value for tolerance, which is 0.001, or you could select any value close to 0. The maximum number of iterations, and then you need to put a step over there. It's like a counter over there. So first iteration will be 1, then second would be 2. Now you would notice something. Pseudocode, for some interesting reason, I can't explain that, but they use the back arrow for storing or defining. Unlike, the CAS uses the front arrow for storing, and most of the programming languages also use the front arrow or equal to sign for defining. But in pseudocode, they use the back arrow. And that's what VCEE examples have also got. Then the sixth thing is now I run into a while loop with a condition, and I'm saying the absolute value of the function at my selected point should be greater than the tolerance value, because if it's less, then I'm saying my loop should stop. So that's my loop condition. Now there are some possibilities which I'm putting over here. So my first possibility is if my derivative is 0, then I need to stop, and I need to give the user a message. So I could say mathematical error, or I could say derivative is 0. So in pseudocode, when we're writing that, all we need to say is that there is an error. And of course, when we are writing our code in whatever programming language, we can actually display what the error is. Next, over here, we are actually running. If the condition is met, that's where it is running the code. Where we are saying the x1 value, the new value, is the Newton's rule over there, which is x initial minus the function value, the initial value divided by the derivative. And then we are saying store this value of x1 as, this x0 as x1, and then keep running the loop. And if you realize that you have reached 20 iterations or whatever you put, and it is still running and it hasn't given you a value, then we want to say, okay, stop and print that it's non-convergent. That means actually the solution does not exist. And normally I put 10 or 15 as my value for n, and you'll always find the solution within 5, 6 iterations. But putting 15 is pretty safe, and if you don't obtain a solution in 15 iterations, then obviously it's not convergent. Then once everything is over, you have to end the while loop, and then we are saying finally go and print what the root is, and then stop. So what you're seeing on my screen at the moment is a typical pseudo code that we would write for Newton's method. Now I'm going to actually use a programming language. The first one I'm going to do is write the code in BASIC. Now I've got two screens over there. The first thing is I have actually defined this code, defined a function on a notes page. So I've defined this function, and I've determined the derivative, and I've given the value of e as 0.00001. So that's all on the notes page. Now, interestingly, whatever you define on the notes page or on the calculator page, TI Basic is pretty smart because it's talking to that particular page. It actually picks up those functions from there. So you will see in my code, I'm actually not defining any of the functions because I've defined them in my notes page. So I'll just demonstrate how you will get to that. But this is my code over here. So I'm saying request an initial value, which I'm saying, let's call it B. Now that is a user input. Request the number of iterations. which is n, and then I'm running the for loop, and I'm saying, okay, display this as a matrix. So m is the iteration there, and that's the x value rounded to 8 places. And then I'm saying after each iteration, store it as a new value v and n there. Now, obviously, this is not a complete code because I haven't put those other conditions when it should stop and so on. But I'm now just going to go to my calculator page, and I'll probably just go to where I've got the code. That's the one in Python. That's the one that I'm running. So that's the code I just demonstrated that. And if I just go screen here, this is my notes page where I've actually defined the function. And this is where I have written the code. So all I need to do now is do Control R over here. So I'm going to run it. So Control R, and I click Enter. Now it says put an initial value. So let's go and put an initial value as 3. And number of iterations, I'm going to put 12. And you'll see it runs the code, initial value, number of iterations. So my first x value, the y value determines, the x value is 16, it moved away, then it started converging. It moved to 9.7, then 7, 6, and so on. And you'll see at that stage, at iteration 7, the values start repeating. So basically, after 6 iterations, I did have a very good approximation there. So that was a very simple code. Now I'm going to demonstrate. I'll just go a screen back, and this is the proper code. So I'm saying Newton's code in BASIC. Now over here, actually, I'm putting all the conditions. So now you'll see I've got if my y value is greater than 0, continue running the loop. If my y value becomes less than 0, stop the loop. So I've got those things. Now, if my derivative is equal to 0, then I want to stop the loop there. And finally, if it meets all the conditions, it will go there. If it's gone past the number of iterations I specified, then I'm saying stop there and display non-convergent. So this is the complete code over here. And I could run it for different values there. So I'm going to run this code, and here let's go and actually in this case I'm defining a function. So let's just go and do x squared minus 5x minus 7, let's say, and initial value I'm going to put as 8, and tolerance let's go and put 0.0001, and number of iterations I'll leave it at 15, and you will see it found the solution after 4 iterations. Now you will see, because I put all the conditions, the moment it finds the solution, it will stop. It didn't have to go to the 15 or 16 iterations that I put over here. So iteration 1, 2, 3, and 4. So after 4th, you'll see it will actually start repeating. So that's the proper code over there. And you can see this is the output that it gives me, the initial value, the tolerance I put over there, the number of iterations, and the function I put in. This time I actually manually put in the function. So the user was asked to put in the function. It calculated the derivative itself. All I had to do was to go and put the function there. This is another code that I have written in BASIC, which is basically very similar to what I have just done. So over here, it's saying I'm requesting the user to put in the function. So I won't run this. It's very similar to the one I just did, except that I didn't put the conditions over here. So if I run this one, and I use the same one, x squared minus 5x minus 7, and this time I'll use a different point. Let's use 9, and iterations, I'm going to just keep it to 7, and let's see if it does that. And yes, it does. So you will see it started repeating over here, but this time I didn't specify the condition, so it actually runs all the iterations. and it's stopping at 4.494. And I want my loop to stop, the moment it starts repeating. That's why this particular one that I put is the best one, where I put all the conditions here. So I've given you three codes that you could use in TI Basic. Let's move to Python. And this is now here in Python. And I'll actually start with the simple one. So Python also actually can talk to the notes page. Now, I've just put these colors over here. These are the inputs which I'm defining. So I'm defining the function in the notes page and iteration. Now, what you see in the blue text boxes over there is actually an output from Python, which is going into the notes page. So those are calculated values. And the last one is just the result that I'm going to demonstrate. That's what I should get over there. So that's my function that I have defined. So I can change that function. I'm hoping you can read that. So the user inputs the function, and the calculator is determining the derivative for that, and number of iterations I've put as 16. So that's the user input. And these outputs that you are seeing are actually coming from my Python code. So over here, it's slightly different. When I'm using Python, the first thing is I have to import the system module. Now, Python works on modules, and I'll just demonstrate that for you for a moment. If I go to Python and I say new, and I'll just say test over here, and I'll say blank program. The first thing is when you go here, you'll see there are several modules. So there is the complex module, time, system module, and these are the other default modules, maths, random, plot, and so on. So Python obviously is expecting you to put certain modules for it to function. And it's pretty user-friendly, Python. So if you look at the controls, for instance, it will actually, and if I want to use the for loop, you'll see it actually does the indenting and everything there. So if you start using Python, you'll find it's very user-friendly. So I'll go back to this over here, and it's the same code that I had previously. And obviously, I'm not specifying anything. So you'll see it's a code that I've written in 13 lines. Actually, it should be 12 lines because that last line is not there. So you can see it's 12 out of 13 because my cursor was sitting there. It has counted that. So here we are saying from the TI system module, I want to recall certain values. So you'll see I stored a function, and I'm saying let me call that function as t, and let me call the derivative as dv, and my initial value is v. And then I'm actually running the for loop, and here I'm saying output that value as v each time. So this is simply the code, and then I'm finally saying go and print that result. So that's the iteration there, and that's the x value. And each time I'm saying I want to store it, and this is a value that's going to my page over here. So those values are coming from the calculations over here. So let's run this over here. And initial value I'm going to put as 5. So it's a user input. And you can see it actually determined the solution straight away because I put a point very close to the actual solution. Probably the actual solution is 5. So let's do again. So that was not a good one. So let's do Control R to run it. And I'm going to put the initial value as 9. And now you'll see it actually gets to the other solution. So that's in Python. But once again, as I said, that's not a very good code because I haven't specified all the conditions. So if I go here, this is my code with all the conditions that I've specified. You know, the if conditions. If it is true, then continue into the while loop. This is the proper way to run the code. And over here, you'll see I'm actually entering and defining the function. Now, Python, you have to use the, I'm typing x to the power of 3. So I have to put the multiplication symbol twice. So that's the power symbol there. Minus 5 times x minus 9. So that's the input in Python for the function. The downside of this one here is I'm actually inputting everything. Now, if I put an incorrect derivative, then I'm going to get incorrect results. That's why the second option was better by predefining the function and its derivative on the notes page. So I can't actually make these errors. Rest of it is all those conditions. Now I'm going to just run this. And I'm going to put my initial guess as 7. And tolerable error 0.0001. Maximum steps, it may not go up to that. So I'm going to put 15. And you'll see it found the correct solution in the 6th iteration there. In this case, the answer was 0. So it started from 83, the initial X value kept decreasing. And finally, I got that. Oh, sorry, that's the value. Those are the Y values. So the Y value approaches 0. So my solution is, sorry, this one over here, which is 2.85 519,654. So it's rounded off the answer there because I specified rounded off to certain decimal places. So that was my code in Python. So if I go back now to my PowerPoint, just to conclude. Yeah. So that's the very simple code that I demonstrated, the basic code. So you will have this PowerPoint and all the codes are there in details. This is the full code in basic that I used with the tolerance, and it goes on to the next page as well. So you can see those are the extra bits. That part I've just repeated from the previous page. So if I just go a slide back, that screen and this screen is the same. So that's where you end the code. So that's the full code in basic. This is the code in Python, the simple one. So that's the complete code over there. And this part I defined on the notes page. Then this is the detailed code, which will go on to another page, which I demonstrated for you. So that's the full code there in Python for that. But it is not an expectation that the students should be writing codes. As I said, they could actually use the list and spreadsheet option for an assessment if they were doing Newton's method. But it is always good to, if you've written a pseudocode, why not test it? So that's the reason students could probably learn some coding in BASIC or Python. Python is pretty good actually once you get your head around it. You could actually do certain investigation tasks on this. So the first one I've got over here is just an example. It says use your knowledge of differential calculus and recursion to determine the approximated value for 11 to the power of 4/3. Make an estimate first, suggest an algorithm, then represent your algorithm as a pseudocode using the 5 essentials. And with the help of cache technology or otherwise, so they could use coding, they could use the list and spreadsheet method. It says determine the value for this to 8 decimal places. And then we are doing another value. We are doing the next one, 11 to the power of 12/7. And then we are saying actually go and determine the ratio. So it's a good task. There is another task I've got over there where you're finding the function and its inverse, and you're actually trying to find the point of intersection for the function and its inverse. So pretty much a similar task. So that's really the session for today. If you have any questions, I'm happy to answer. Brian, are there any questions?
There's been quite a few along the way, Sanjeev, which is great. It's always good to see people actively involved there. And there's a couple that I'll probably easier if I address as well. But thank you very much for the presentation there. And I really like what you've done there. You've given us a lot to work with, culminating, of course, with the final idea of investigation tasks. Investigations themselves, of course, coming under the spotlight in the study design review. But what I like, I confessed earlier that I've dabbled with a bit of coding, but I by no means claim to be at the level that you are, or have any particular great expertise. As you said, the study design isn't forcing us to use those code languages, whether it be TI Basic or Python. Pseudocode itself was illustrated quite beautifully in what you showed us. I'm just going to grab the control here, Sanjeev, because I want to share a couple of things too. But you illustrated it quite beautifully with the spreadsheet and the notes applications there. That iterative algorithmic processes, that works. And I like that. I'm confident with that. So I'm just setting up my share screen to do a couple of things here. So one of the questions that was asked was, how do we access these coding languages if that's the direction you want to go in? Now, I'm aware that a lot of teachers and students, when adding application types, tend to go back to this home screen, because we've got these little icons here to add a particular application. But as the operating systems have progressed, there are more than the, what have I got, 7 here. If I'm in a particular document, I'll go in here. Or hang on, I'll do that again. I'll just go new document. When we open a new document, you can see that we get more. We've got there's the 7 that were on that home screen up to the data logging, but subsequently there's been widgets. There's the program editor. This is programming in TI Basic, and then beyond 9 we've gone to A, which is now Python. So let's say, for example, you're working on a calculator page and then you wish to add in a programming application. Do not press the home key. I know that you can add application types by doing that, but it's not going to get you to widgets or TI Basic or Python. This is not my preferred way of adding a new application. My preferred way is, there are several ways of doing it. I tend to go Control and then this document key, Add Page, because then at my disposal I have all of the possibilities, including the TI Basic and Python. I also tend to think that, cognitively, if I'm already working in a document, then to be going back to the home out here, that to me seems to be going out of the document. So anyway, I needed to put things in there, but you've got the idea. So I don't like the idea of going out of the document in order to add more into it, so to speak. So that's my comment there. So thank you for the people who were asking questions about that. The other thing I was just going to give a bit of a plug was for the upcoming webinars still in this series. It's been very, very popular. Remember, you can review all of these. If you go to the TI Australia webpage, you can watch the past webinars on demand. So they're all recorded. They're all there on the TI Australia webpage, as well as on our YouTube channel. And there's been massive numbers of hits on that. Coming up next week, well, that's probably it now for the methods series, but we have 3 in Spec Maths next, or coming up, one this week and 2 more next week. So we've got lines and planes in 3 dimensions, and next week sequences and series, and as well as arc length and surface areas of solids of revolution. So thank you again, Sanjeev.
My pleasure. I think most people wanted to know if this file would be available. Yes, I shared this with the TI, and I think once they upload the video, they also put the related files there. So I think you should have access to the PowerPoint as well. Am I right in saying that, Brian?
Absolutely. So what you share with TI Australia, our web manager here, Peter Fox, he can send that out to all of our attendees. So that will be links to the PD certificate, links to the recording of this webinar this evening, as well as the files that you will very graciously share with our participants. I just on to adding on there, if you don't have all of those applications, including, so check on your calculator or your software that it comes down to add Python. Check that on the TI website that you actually do have the latest operating system. The latest OS is, I think, 5.4 from memory.
Yeah, 5.4, correct.
Yeah. So that's where you can. So this is the front page here. That's where you can update that for your software as well as the individual handhelds. While I've been sharing my screen, Sanjeev, I don't know if there's been more questions coming in. I have seen a few thank yous flashing over the screen there. Great presentation. Thank you again. And thank attendees for staying with us at the start there where we had our audio issues, phone lines underwater. I don't know what, but thank you for staying with us. Terrific presentation. I really like those sorts of algorithms. And I think it also highlights it. It's these sorts of algorithms that are behind the apparent magic that a lot of the calculations do when we find roots and intersections and maxima and minima and so forth. I do remember in older technologies where we were actually asked to specify a guess. And I like also that you highlighted the importance of selecting an initial value for the iterative process, that initial guess, so that the algorithm would converge rather than oscillate. So you very beautifully showed us that Newton's method, as much as we love it, may not always work. We need to work in partnership with it to select an appropriate value for the start. So again, thank you all. And we hope to see you again, either for the specialist series if you are teaching those, or maybe in further webinars. I don't know if we have more for this term or for next year. So, and of course, can I also plug the Learn, Energize, Connect event that will be in Melbourne. I don't recall the date. I think that's going to be the 31st of November. Yep, 30th of November in Melbourne. So check check the newsletter for that one, where we'll be going through a lot of this stuff again. Terrific. So thanks again to all, and